Welcome to the evening of a very important landmark event, not just for the university, not for the research community. I think this is a landmark event for our species. I mean, you laugh, but to say that we are here to celebrate an important scientific discovery of our times, I personally think would be an understatement. What we are celebrating is the recognition of a fundamental change in the history of our species, in our consciousness of how we view ourselves. It's a common story. For thousands of years, we as a species have always wondered about life elsewhere, about planets elsewhere. It's humbling to realize that not until 25 years ago, just until 25 years ago, we knew of no planet outside the solar system. Imagine living in such a world, and many of you have lived in such a world, when we didn't know of the existence of any planets outside the solar system. It is in that sort of framework that the first discovery happened of a planet outside the solar system, and when they first discovered it, it was nothing like what we see in the solar system. And the story that we are about to embark upon, and our guest here is going to take us through that journey, is one of immense passion in science. So I want you to follow the talk very carefully to pick out that passion that's coming out of this fantastic story. It is equally a story of enormous tenacity, enormous grit and determination in the scientific pursuit. But of course, we need that to solve any big problem. But when you couple the determination with the passion for science, it yields the results that we are going to see today. I want to specify one other thing, in addition to those two aspects, is serendipity, is that fundamentally, nature has to be kind enough to reveal its secrets for a prepared mind, right? So we are going to see flavors of that as well today. So the Nobel Committee did a wonderful job of defining I mean, you laugh, but if you read the underlying theme there, it's improving our understanding of evolution of the universe and Earth's place in the cosmos. I work in an astronomy department where we have both exoplanet scientists and cosmology researchers, cosmologists. And you usually see those fields as very different because they are at the opposite ends of the size scale, at all scales, right? But to bring those two things together says something specific about our psychology as a species. So finally, we are trying to put two and two together, see this as one big picture, both our own understanding of our place, the Earth's place in the universe, as well as answering big cosmological questions within the same framework. I would like to introduce Professor Didier Queloz, who is sharing half the prize, half the Nobel Prize in Physics with Michael Mayor for discovering the first exoplanet orbiting a sun-like star, right? And he will walk you through all the details of his discovery, but it has been an enormous journey since then, since that first discovery, which discovered a planet nothing like what we see in our solar system, to today we know a few thousands of planets of all kinds. Professor Queloz made this phenomenal discovery when he was still a graduate student, so that's some motivation for all the graduate students out there. As a graduate student at the University of Geneva, and it also tells you about the kind of science this was. It's just he and his supervisor trying to pursue these objects and made this phenomenal discovery with a very small telescope, actually, by modern astronomy standards. And ever since, he has gone from success to success. He's made many other discoveries, including one of the first transiting rocky planets around another star, and many more discoveries to his name. And after his graduate school in Geneva, he spent some time in Pasadena, and then recently, 6 years ago, he moved to Cambridge to take a professorship at the Cavendish Laboratory. So it's our great privilege today to welcome him to share with us his exciting journey in exoplanet science. And it's only fitting that we are here at Cambridge listening to this great story, a place which has seen some of the greatest discoveries in modern physics, all the way from a century ago. So it's an honor to welcome you onto the stage to share with us your exciting journey. Please, Didier Queloz.
Trying to fix the HDMI cable, that keeps us some trouble. Well, I think when you get to such elevated recognitions, I think it's a gift, and that's a gift for not only me, but that's a gift for the community, and that's a gift that I would like to share with you tonight. And there's something that is fantastic. We've been talking about something that happened 25 years ago, which means I'm sure that a graduate student that you're looking for, that was like you. So, it's quite interesting to see, the beauty of the science and the surprise that we can get. So I'd like to share a little bit, in a very informal way, this Nobel Prize with you. And actually, everything is very casual here because Maddie came in my office just before lunchtime, and he told me we have to organize something in Cambridge, and would you be able to do that? And I said, yes, please. I have plenty of time today, I have nothing to do, so you can do it. And you can do that, everything was on, and we opened the registrations, and then 1 hour after later, I learned it was fully booked. Otherwise, I'm really shocked. You can see that there's so many people that was interested, so I hope you will not be disappointed by the number, because I just really what about before, trying to collect some kind of idea to share with you this slide. Okay, thank you. So it was mentioned before, there is something like beautiful here that has been acknowledged by the Nobel Prize that I think is worth to be mentioned specifically. Is we're combining different kind of scale. We have the Seymour on the left, who is dealing with a great scale, with the biggest scale you can imagine, this concept of dark energy, dark matter, and we have Michel Mayer and myself, which is dealing with something which is detailed, which is practically the planet on stars, and they capture the idea that we are exploring a kind of new dimension, and theoretically, and we've been together in this kind of a concept that we explore all the aspects of the cosmos, and I think it's a very strong signal they're sending. It's very interesting. It's also a pleasure to always be reminded that astrophysics is part of the physics. Physics Nobel Prize, and you may remember that there has been a couple of recent Physics Nobel Prize awarded for astrophysics work. So I do a little bit my promoting work. If you like physics, you can do astrophysics as well. Okay, so what are we talking here about? Well, we're talking about planets. So this is the planet that we had in mind, everybody has in mind, and we were talking about 25 years ago. So it was the only perception we had, and actually these are fascinating objects, and they were studying by itself, and there has been a lot of space probe to explore this planet. And the story of the discovery of the planetary system is a very fascinating story. As soon as people wanted to just realize that they were orbiting the planet, orbiting the sun, they started to really trying to assemble this into a formation model and trying to build up the whole concept that what was the history of the solar system and how could you build a planet. And in the late 70s, 60s, 70s, I think that the community of astrophysicists were pretty pleased about the understanding they had about the planetary systems, all planetary systems. And then the questions about planet and other stars was pretty obvious for everybody. We should have similar planet that we have in the solar system, because we always have these preconceptions in physics that there's kind of rules, applies, and something there's kind of a standard model, a standard concept, a statistical model, and then we should be about the same configuration. So the whole idea of looking for planet was practically trying to look for something like our solar system. And you can look back at the first time, which is the first time people started thinking about the way they can approach the problem, almost 100 years ago. So in terms of physics concept, that there's nothing really extraordinary in that much more profound concept. The idea is pretty there for a long time, but it took a long time to get there. So I'm going to get that image. Okay, this is very hot. Why? Okay. Right. So the reason why, I mean, we had a pretty good understanding of the concept of what is solar systems, what is our solar systems. The light is not too much. Maybe a little bit of light would be nice to see a little bit better. The reason is the idea that we form solar systems comes from a structure that we call a protoplanet like this. This is what you see here. So here you see the state of the art that we can more this one, not the one in the room, but this one here, that one here. I don't need to be so much like a VIP star. So the idea is we have this clear concept that the planet all form in this kind of system. This is a very terrific image, and that has kind of a completely changed perceptions that we have of the formation size of the planet. I don't want to discuss this too much, that's not the purpose of this talk, but I want to mention this. And the reason why I want to mention this is we have a kind of connections between the origin of the planet and the way we saw the solar systems. And all this is connected pretty well, and you assemble the mass around the stars, and then you aggregate the star, and you build up, it's a bit like a Lego game for your planet. And you have a good idea why you have the planet like Jupiter further away, because you have a lot of ice, because it's cold, so it's easy to make a big core of ice. And then you build up this big planet pretty quick, and then you take anything you have, if you make massive enough, and you build up a planet like Jupiter. Well, if you're too close to the sun, well, you don't have ice, it's too hot, and then you have to deal with kind of people or dust, anything you have to glue it together. It takes a very long time, and by the time you reach this, a lot of the material that you don't see, which is gas that is remaining around, the same gas you have in the sun, is gone, and then you just end up with a planet like the Earth or Venus or that kind of planet. So that was really this idea, and people were really kind of focused and obsessed to find planets like that. So what happened in 95 is we had this concept of the solar systems, and I will use that's the solar system, it's great to give an idea of what we're talking about here. Oh, before I want to show something which is interesting, there's something which is quite interesting when you look at this disk, but on the side this time, you realize that it's pretty narrow. And that's, there's plenty of the reason why it's narrow like that, but there's something magical like being narrow, it's not only having a lot of structure you have, it's extremely compact. And then this is the reason why you end up with a system which is into the disk, because most of the material gravity and stability region is very thin. You have this very thin disk that is the origin of the formation of the planet. Now, on the most simplistic concept possible, you can draw that kind of diagram where you set the distance of the planet from the sun, from its star, and you know the mass of the planet, and you see it is 1, which is the mass of Jupiter. And that's really the concept that we had about planetary system. And when I started the program, that's exactly the concept that I had in mind. And the funny part of the story is the equipment that we built and I designed as part of my PhD and all the data analysis and processing, in a way, when the program was started, my PhD advisor told me, you know, Didier, you're not going to find a planet, it's going to get the Earth. You're only going to find it on the top, which is Jupiter, and it's huge, quite far away, so it takes a long time for that planet to go around. So of course I was just barely 1 year before the end of my PhD, and it was obvious for him that there would be no detections, and he was so convinced about that he went off to a beautiful island with my wife for his sabbatical, and he gave me the key of the equipment, and I said, okay, just start the program, and I said, that's fine. I did the equipment for me, it was so much fun. And I have to tell you, so a lot of people say, well, you were surprised, you found it by mistake, the way you did the That's true, we were surprised by what we found, but we were looking for planets, but I was just very happy to start the program. So the first piece of advice I have for any of you that wants to do any program is that if your supervisor will tell you something, don't listen. We will call it tomorrow. So I started the program, you can imagine my surprise, when after a couple of runs, I found this star, which was 50 by day, and that star actually had a completely erratic pattern of the living, and I got completely kind of obsessive for the very good reason, because I panicked completely, because it was the end of my PhD, I did all the software, I mentioned the instrument, and the instrument wasn't working properly. So I had to find out what was going on, and I realized that after quite a lot of intensive analysis of the data and reobserving again that nothing was wrong with the equipment. That was a start, actually, I was wrong in a way. But I was so insecure about all this, I decided I should better put that under the carpet because I was not very good for my PhD. So anyway, I said, well, now I was enjoying myself over there. So I didn't decide, I didn't talk at this at all. Until I think I had a good understanding into it. And after some time, I realized, yes, I mean, it must be real, it must be a planet. Which was just absolutely unbelievable because the theory was saying that it is not possible. But then here I was lucky because I was a little bit, let's say, stupid, but I didn't really know it wasn't possible. So sometimes don't have to too much theory. It's good. It's enough, but not too much. So I was convinced I found that, and then I sent this back to Michel. I think I found something that is not to Michel, and Michel had this fantastic answer. I remember he said, yes, maybe. Well, anyway, I'm going back to the analysis together. Well, actually, what I didn't tell me at the time is it didn't really at all. I couldn't understand the theory, and much later on, it wanted to be nice. So second piece of advice, I love the PhD supervisor, always be nice. Then we work together, eventually we get this, and then we know the rest of the story, and we observe this. So that's the story, in the short way of the story. So I thought I would try to bring you back in time into this story. I want to do that in a very nice and soft way. So I will show you a kind of a mashup of a movie that I picked up from old movies that was, some of them are pretty old from the time of discovery, very close to the time of discovery. But since we are in the UK, I thought we had to make a musical way. Okay, let's try. So the song I have to fix it. I hope the HDMI will be nice with me. Let me just get this, and it was going to work. So, it's a couple of minutes, let's try it. Well, that's 51 peg where it came up here. So that's why it was such a much surprise, this 4 peg. But I will show you the movie is much more interesting to see this way. Okay, and then I need to do that, I guess. Yes, back in time, 25 years ago. Sorry, I don't have sound, I love it. The sound doesn't work, and let me just do it again. Technical problem? I hate this. It was working before, I don't know why it's not working now. Let me just get this right. Okay, I have to do that. The sound disappears when I plug in this HDMI. I think the stuff is this. This is the problem I'm having. Let me get the sound, maximum sound. Here we are. Let's try it again. Did we get it? Okay, let me just get the mic. Here we are. Yeah, should be working. Yeah, we should bring the light down. Yes, way too much light. That's true. You get the sound this time? No, it was working before. I can't believe why it doesn't work. So this, that's not for me. I love this equipment. Let's try again. He knows. Good.
Hopefully. Otherwise, I'm making a fool of myself in front of everyone.
Yeah.
Where's the...
Oh.
And then we just have to choose the right one.
Oh. The output.
And then you play it one of you.
Let's try it. Oh no, it's not this one. Try to do it this time. Okay. I told you it was prepared 2 hours before, so it's just don't expect. What is going on? Ta-da-da. I hope I'm gonna get this on. That's me! In case you did not recognize us.
Green men, I don't mind them. If only they'd look closer, would they see a pure void?
Look at the screen. The size.
They'd find out.
You've never seen such a screen, huh? 25 years ago.
In fact, the first reaction you have at that time is, oh, something is wrong with the experiment. You never think about planets. And we had to wait up to July. And then we had the curve, the wobble, we had prediction, and we had to wait.
Was a world running off pulsar that's true, where the news is a sun-like star with baubles of wind and precise to be the time. No clue, not a spot, but you like the clouds. You're gonna love the sky. Orbit traced every 4 days, hot as can be. Or to Jupiter size was something of a surprise, especially given its star's proximity.
The first reaction was enthusiastic. It was a creative time with calls from papers, from television, from radio, from all the world, and email, 100 per day or something like this. It was absolutely completely time where we have no possibility to work at all.
Yeah! Okay, so you get the pitch now, what we did, 25 years ago. So what is interesting here is to compare where we stand today, right now. Because there's something that happened there, is when we announced the discovery and it's also shooting from the Florence meeting, there's a lot of magic in the story, because we made the announcement of Florence with the city of Bengal. So it just happened to be like at that place, and it was a big surprise for most of the people. Here we were listening and answer questions and the people were enthusiastic, but actually, the first couple of years, it was really tough, because I think very few people really didn't believe that stuff, because they thought they had some conversational stuff, and really had to fight quite hard to be convincing. But what happened is, of course, this moment when we announced the first time, everybody realized that they may be plenty of others. And then shortly after, other teams on the other side of the Atlantic started to discover planets. And we all know right now that there is really a lot of planets found over the star, but there's something which is pretty much interesting. We see one planet was so special compared to what we have in the solar system. So it was a big puzzle for the theory 25 years ago, and it's still today a puzzle for the theory. And most of the planets that we have found so far, that not really fit in the picture of the solar system. It's a big deal what I'm trying to capture. This is the size of the planet, this is the techniques in transit, and give you a little bit of a flavor. We have on the top what we call the hot Jupiter, losing 200 kilometers. There are all these populations of objects that are between the Neptunes, mini-Neptunes, and Earth. So most of these planets have a counterpart in the solar system. We don't have any Neptunes with a 20 years orbit. It doesn't exist. And in a way, the discovery of 51 Peg was already a kind of advanced warning signal. So there are stuff over there that we have no idea about. And we had, in a way, constructed a whole idea, mental picture, or should be a planet, that was entirely wrong, and just based on only a single example. And that's one of the revolutions going on. We're trying to encapsulate that in a more global theory and trying to understand what it means for the solar system itself and for the origin of the solar system itself. So to give you a bit more, another way to see that, well, that's the hot Jupiter, and that's what I was mentioning before. If you did the math, which is a similar technique, which is the you have also the same kind of population. They're not really fully complete. You have a lot of bias in that. I don't want to discuss this. You have also a more massive object that look a little bit more the one we have in the solar system. It's all this Jupiter population. But if you look in detail on this Jupiter population on the top right, which is actually that one, you realize that most of them are very weird orbit. It's what's called eccentric orbit, which is very different from the orbit in the solar system, which is very circular, which is also something that they make quite different. So amazingly enough, the first discovery of the planet on the star was found entirely different from the electrical system. And 25 years ago, we had about 4,000 planets, which people didn't know. We still left on the same conclusions. So we really acted like a trigger and trying to open the new dimension of the universe, which is something that we quite working on, an idea of the number of telescope time people that have worked to achieve that kind of discovery. Another interesting aspect, if you only look around and ask yourself, how likely it is when I look at the sky to find a planet? And if you do a quite significant advanced statistical analysis and try to correct all the biases and all the elements, this is the number we got. So, in a way, the hot Jupiter, the one like 51 Peg, is few percent. So, here comes the rock. When we started the program 25 years ago, we shared many other stars, but we decided that it would be better to focus on 20 stars. So, you pick up 20 stars, which is the brightest in the way, and the piece of rock was amongst the 20 stars, we had 51 Peg. So with a probability of few percent out of 20 stars, we have been lucky. It's a good sigma detection, for those of you that know what it means, which means it's a piece of rock we get every month. Not too bad, but think about we toss a coin every day, and then we get something. So I think we've been lucky, and I do think that this is part of the discovery process. Luck is an element that plays a role. And that's the reason why we scooped everybody. Because out of this object, we have a perfect machine, we have a perfect data processing, the object pop up pretty quick, and practically 6 months after starting the equipment, we had it. So that was really the element of piece of luck, in a way, that we had by having this object part of the strategy. Now, if you want to get a new perspective of what we know about this, most of the solar system that we have around, that's the way to see it. If you try to scale up the solar system, it's more shrunk, and it's not much, but to give you a perspective what we're talking about, most of the systems, I should have said that before, but most of the system, small system we're picking up, they practically would fit within the orbit of Mercury. So we had kind of a strange situation, because all this idea to look for other worlds was directed at the idea to find other systems like our solar system. But actually, most of the planets that we found so far, they're entirely different from the solar system. Well, it doesn't mean that there are no planets like the solar system. It means just we have not found yet the system because they are difficult. So nature, in a way, made a gift to us here. Because you can imagine that if you had only a system like the solar system, I mean, I would want to business would have changed field or changed the topic and doing something better. This one has not exist. So that's interesting about it. And we're so successful right now in science, and we're asking questions about the nature of this planet, the structure of this planet. We come up with this kind of weird concept of union, super Earth, nobody really knows what we're talking about here. That these systems exist, and they are very interesting to study and to understand in a way why in the solar system we don't have this kind of object. So I like to finish to give you a little bit of an idea about how can we move forward, how can we continue. And I would like here to just give you a hint that what may happen in the next 20 years and what we could hope to detect if you're trying to look for a planet like the Earth. So to come back to the detection 25 years ago, when you look for a planet, this is a kind of signal you want to detect in radial velocity. So you measure the speed of the star, radial velocity with time, and you see that in the diagram, you see the ephemeris and the dots filling up, which was exactly the dots of the measurement we had. Now, the problem we had when you look at small systems is the star is not helping you, because the star has a lot of structure, and as a lot of structure and activity you have in the star. You have the spots, you have the flares, you have a lot of structure in the stars that prevent you to get a very stable measurements of the radial velocity. You don't really care when you detect a planet like Jupiter, because the effect is of the order of a couple of meters per second. It doesn't really affect you. But when you go for a very small planet, it is a real problem. And to give you an idea, what the sun does, this is the variability of the sun. And the speed is kilometers per second. So you see the variability of the sun is the order of 1 meter per second. So the sun is shaking at that level. And that's the reason why it's so difficult today to find a planet like the Earth. But nobody can stop the tenacity and the focusing or the way the idea of a science to try to promote new ideas and to do better, what I usually call the obsession of the result. And we're trying to deal with that, and we're trying to develop a further program. And I would like to mention the program that I started with a lot of universities right now. I'm not one of them here. That's one of the reasons why I moved to Cambridge. One of this project I'm sampling. You see all the list of the universities which are working on this. What we've done is trying to start with the same techniques we did 25 years ago and trying to move it ahead. I could have discussed many future programs and I just decided to pick one because that's the one we were doing in Cambridge. We're investing a lot of time and energy, well I know, based on a concept that was developed 25 years ago. So I would like to end my talk here and heading to Matthew by telling you that I hope that you enjoy the idea and manage to community this kind of emotion, this kind of idea that science is fun, science is, don't be shy of dealing with a difficult project, emotional project. I remember all my advice. Don't be sad. Thank you.
Nice, Steve.
That's the scary part. It's like an exam.
You're ready.
So now any example is hard to practice. Natural sciences, find out. So this is going to be an informal Q&A session. The way we'll operate is I'll ask a few questions that come up in my conversations with students and public alike over and over again. So I'll sample a couple of questions and I'll ask you. So that'll take just 5 minutes, 5 minutes. And then we'll open the floor for questions and we'll go to any questions you want to ask. So first off, I would like to ask a very broad question that whenever you talk about exoplanet science, the public at large and scientists have this one thing in mind, which you also showed me in your last slide, the detection of life.
Yes.
Is supposed to be the holy grail in a way of the field. What are your thoughts about that in the sense of how common do you think life is out there and how likely is it that we'll find it and when?
Yeah, I mean, it's a very interesting question because dealing with life is something we're dealing from the very beginning. Because even when we announced the first planet 25 years ago, we had a lot of questions about life. It's kind of it comes with the planet. So I think we really think planet, we think about surface of the planet, and then we're thinking about life development. It comes together. And even as astrophysicists, when we know that most of this planet and this one, the one that was found 25 years ago, clearly has no life, it's an appeal. I mean, it's definitely an appeal, and it's in the back of our mind. Now, the big change right now that is happening is we are detecting objects that where we can sensibly ask ourselves whether there is some life on it. Because the planet looks not far from the Earth. Some of them are clearly rocky planets. We have strong evidence to claim they're rocky. And some of they may not be rocky, but they can be kind of ocean planet or ocean-ish planet, and they are located at a region where you have liquid water, which is what we usually define just for to get a simple picture, habitable zone. Now, so the question of life is built into exoplanet research, and now it's a topic that people are really dealing with. It was not really the case 20 years ago. You would seem like a weirdo when you start doing life stuff is something that's nobody really talking about that, or you were looking at alien, and that right now the approach is very serious. So there's different perspective into that. The first one is people trying to attack this problem from the geophysics perspective or biochemistry aspect, combining of the origin of life on Earth, where practically what you do is you ask yourself, okay, when I look at the early Earth as early as I can I make up a way to build life as it is on Earth, and can I find some principle that I can test on another planet? And this is going on today. I mean, there are really people, and I'm working here with people, some of my colleagues are experimenting into the lab or developing theory and model to explain that. So there is a serious prospect that to understand better this. Now, the most difficult part is trying to remotely look at the planet and trying to find a connection with some idea of the life we have on Earth. And that's a tremendously difficult question. And I think being sure that there is something living on the planet will take a long, long time, and we may have a clue, we may have a probability aspect, and so it's likely, we're not very sure, there is some strong evidence or weak evidence, but this is going on. But there is something I'm sure about, is, scientists are not crazy people. If they look for something, they believe it exists. So all the people working on the question of life in the universe, typically there are life in the universe. And usually my perspective of this, being not being a chemist, I can easily play the game. I say, look, life is chemistry. So the chemistry is the same everywhere, so why don't we have life everywhere? And I'm a strong believer that there must be life everywhere. But it doesn't mean that life is going to evolve the same way we have on Earth. And I think that's the fascinating question. And that's a fascinating question that the exoplanet research is leading to, but clearly it goes beyond the capability of astrophysics here. We're talking about more combining expertise and combining field, which, by the way, is something that this place, Cambridge, is very good at, by the nature of the proximity of the college system. And that's something we're trying to achieve with Madu and a couple of people. I recognize a couple of my friends, colleagues in the audience trying to achieve that. So, yes, life is everywhere. It's part of the exoplanet, but exoplanet is just one piece of the big jigsaw we have to solve.
So we'll come to many more scientific questions. I don't want to take all your questions, so I'll ask a slightly different one. So you have spoiled it for all us supervisors. I have many students who are here in the audience who are nodding as we're talking. So I want to ask a direct question that I get a lot from some graduate students here and everywhere. In cutting-edge areas, you have showed how you face almost unsolvable problems. You face a lot of frustrations, a lot of failures, and sometimes luck just helps you out, but many times it doesn't.
Yes.
What is your advice, practical advice to graduate students who may be stuck on the problem right now, debugging code for a very long time, not working? Practical advice, what is the mindset that lets you keep going in pursuit of whatever you're trying to pursue?
Yeah, the concept of failure is something that top universities have difficulty to handle with, because most of the people are selected because they're good, and they're not really used to fail usually. It's not something you're used to. But I think this is really what when you start getting science and trying to really embark into a program, that's something you have to experience, because if you cannot deal with failure, which is what you actually do in science most of the time, I mean, you will have trouble really to achieve something. So there has been some scientists, and I wonder whether I should start, which instead of having a CV, they produce a CV failure, which is the list of all the programs that have failed. In my case, I can mention one program. After all this discovery, the early discovery, I was a strong believer that we could do much better by detecting the motion on the sky by the astrometry of a planet. I embarked on a very long program with other universities to try to use this technique by designing ground-based equipment that will do astrometric measurements using a technique called interferometry. I spent 4 or 5 years of my time and my research, and I spent money to find out at the end that the whole idea of the program had to be abandoned because some piece of the equipment was not exactly what we thought it would be, and we would never reach the goal. So this is part of the science, and when you spend a lot of time and money, I mean, of course the failure is bigger, but in a way you have kind of micro failure. I mean, you can have difficulty to solve. So my advice here, if I can make, is I fail most of the time. I have plenty of failure, but who worries about? Because let's focus on the few elements that bring you a lot of positive energy, because you're making a small progress. Even tiny progress is good. So failure is part of the game. So get used to it. That's the idea.
Good. Get used to it. I'll ask one last question, and then open it. Is the process of scientific pursuit of very controversial results or things that you don't know how they will pan out, like you were saying, you also spoiled it for us theorists. You told us you don't believe in theories, so that's fine. But when you are pursuing things that you don't know what you expect to see, and you're seeing a result, how do you convince yourself? Where is the element of confidence that comes? As a student, as a senior researcher, you have some guidance, but as a student, what is it that keeps you going?
That's extremely difficult question. So the reason why I'm a bit joking about the supervisor aspect is I think we should not be afraid to go a little bit beyond the edge. And there's nothing bad about disagreeing and trying to experience something which is a bit awkward, because I think it's part of the game. If you're not ready to take a risk, in a way, I think you're missing the point, because the risk is entirely built into the science, and it should be built in any aspect of the science. And talking about a more senior level, which is the funding aspect, I think the risk-taken aspect of the funding is a true catastrophe, especially in this country. It's almost impossible to build up a funding with a serious risk. The only way to do that is with private money or university money, but official governmental money is impossible. They don't want to take any risk. So in a way, they have lost entirely the idea that science is a risky business, and if you don't accept this, you're not going to win anything. And you know, the interesting part, I have a couple of my friends which are in the business, and they do startup company or this kind of activity. And for them, there is no problem. I mean, they open 10 companies, only one will be successful. They find it's a success. So they have no problem with that. I don't know why us scientists, we cannot convey agency or the government, or that risk is part of the game. And I think we're doing a bad job in that and trying to promote that. Because maybe we too much use the perfections and not assuming the failure. So starting to promote the failure as an element of quality of the research, maybe something we should consider doing. Maybe I could do that. No, I have Nobel Prize. Nobody will challenge me.
Good. Thank you. So the questions that we're almost good. So we'll open the floor. I have tons of questions, but I can always ask. So we'll open the floor for questions. We'll take any questions whatsoever, science, social science, life, whatever.
Yeah. I cannot promise I will answer all, but
no, we
can try.
No, we only that they can ask. We didn't promise they will answer them. So, anyone, so there will be 2 mics going on either side. So there is a question right here, Daniel, right here in the front.
Yeah, that's fine. I mean, just put very close to it. Yeah.
Just wondering, what's your review on Fermi paradox? So if there is a why is so silent, and why is there a big future in the universe that causes huge extinction or something like that? And second, do you think moments exist and what they come to us?
Sorry, what is the second question?
Moments. Is that moments exist? They come to us and say, you know, I'm not one day.
Okay, so I will address the first one. Now, the first one is very interesting because there are a lot of very interesting elements. So those of you not familiar with the Fermi paradox, it's a very nice way to express a very complex problem, which is, okay, so let's imagine life is everywhere. So it's unlikely that we are the first, because we're not particularly old, seen from the universe age perspective. So it must have been other life elsewhere, and of course they must be so advanced that they should have reached such a state of technology that they should have traveled and been everywhere. And then they say, well, where are they? And I think it's a very interesting element, and you can split this Fermi paradox on different sub-questions. The first one, it addresses the idea that, okay, life is something that comes everywhere as a natural process. That's true, but what are the ingredients needed for this natural process? Or the chemistry may be good, but do you have the right ingredient at the same time? And if the ingredient needs to have a special event like reconfiguration of the systems or some water delivery that come at a specific time and not too late and not too early, then you start to add a lot of requirement into that. And if you need a Jupiter as well, if you need this, that, it makes all the ingredients challenging. And we know that it's not so difficult by changing a bit the chemistry in the interior of the Earth to have a planet that is almost like the Earth, but has no plate tectonics. And without plate tectonics, there is no life, because you cannot recycle the atmosphere into it. So I think the question of the ingredient, I think, is essential, and that's something we don't know. We don't know the element of the ingredient. So there's another aspect behind this, is there is this conceptions that when you have life, you should at the end have life like us, and you should be plane and fly into space. Well, this is not very obvious. I mean, not everybody would agree that in any cases you end up like that. Some people may argue and have suggested that the reason why life went out of the ocean is because of the moon, because of the tide of the moon. Whether it's true, whether it's wrong, I don't know. But then you start to add a lot of ingredients, because the moon exists only because we had a very big impact at a very specific time early on in the Earth. Not too big, otherwise bye-bye the Earth, or not too small, otherwise you have no moon. So, you know, is it needed or not? So that the idea that life can evolve is something clever, and that's something that to me is not obvious at all. And in a way, it reflects to this search or SETI search, where people are looking for civilizations, because that's a bit what they're expecting here. But then there is a third aspect that Fermi is asking is, well, let's imagine that it's pretty common to have life, that at some point or another, even if you don't have exactly the same configuration, you will evolve life, and you end up with something that will be able to fly in the other space. Now, could you survive when you reach a technology capability that allow you to travel between stars? Implicitly, you have a technology that is enough to destroy yourself. And that's what we know on Earth. And if we reach that level, we have the capability to easily destroy yourself. So how long could we sustain this situation before we actually destroy ourselves? Well, when you see what's going on with the global warming right now, I think the question is very valid. So all these are very, very interesting questions. I have no answer to any of them, but I think Fermi is pointing to the right element. So whether you like to point to the social element or the interesting nature, when you become clever, you are so dangerous that you kill yourself. It's kind of the end of it. You create something maybe interesting on that aspect, but it's just disaster in terms of capability. Or there is some element to the life evolution that we don't know. Well, the good news is I think we know all of them. The first one is I think if we don't fix the climate warming problem within 100 years, we will know very much that that's the end of it. So this we know, I can tell you. There's no doubt of it, and it will certainly be the first question to answer. Can we design as a society, as a civilization, something that is sustainable? Whatever you call sustainable, that's really the idea. And that has any hope to be sustainable for 1 million years old. Now, the aspect of the origin of life, I do hope that with all the work being done, there will be some progress. It will still be tremendously difficult to assess exactly the detail of the life evolutions. No, about all the elements, about the statistics, all the chance, I think we will never know, because we will never know exactly what happened at the origin of life on Earth. We will be very close, but there will still be element which is unclear. So I think Fermi was a genius by setting this paradox, because it opens so much possibility of very nice discussions. So I just love the Fermi paradox for that reason.
So, a question? So let's take one in the very back there. You got the mic there?
So this isn't really my own question, but I still don't give the answer to it. So the question is, in some corner of the universe, there are alien astronomers with similar technology to ours, looking at our stars right now. Could they have any idea? Okay.
Technical issues.
Okay, so if some corner of the universe, there are alien astronomers with technology similar to ours, they are right now pointing their telescopes at our tiny star can they have any idea that there are some life forms around it, that they are intelligent enough, that they are actually capable of looking into the stars and wondering about it? This is not really my own question, but I really don't give an answer to it.
Okay, yes and no. I think they will get some idea about the solar system, but they will certainly not be able, I think with the current technology, to say anything about the Earth itself. But they will pick up Jupiter, they will just identify this as an interesting system. Now, if you really use the current technology, there has been the SETI program, and the SETI program is exactly built on this idea. So if you have exactly the same civilization than us, producing the same amount of radio emission at the same time, because it may not last very long, because radio emissions tend to vanish when we don't use it. But you imagine that we want to detect this, and you should not be too far away, because otherwise we don't have the size of the antenna to pick it up. We would have detected it. That was the whole idea of Carl Sagan. It was to do that. And that was a very good idea. I think doing this on the hundreds of nearby stars to look at an obvious signal was exactly doing what you're describing. It failed. Didn't detect anything. I know they're moving to the millions and millions and millions, and I think the statistic, the probability is just getting very down right now, right? But that's exactly the idea. So yes and no, it depends what you want to look at.
Other questions? So we'll take one from the middle here.
My name is Aino. I saw I think your interview with the BBC, and you said you were quite surprised that you win this prize.
Yes.
Because the discovery was at the South Africa about 25 years ago. I'm just wondering, in your view, what do people see differently today, the enormity of your discovery compared to 25 years ago? Why people suddenly wake up?
That's a very interesting question. So I need to think a bit more about that, but I can give you some element. Maybe you will find the answer yourself. Some element is most of the exoplanet community. I receive really a lot of email, and a lot of them are saying, "Oh, finally it happens." I mean, for everyone, it took way too long because there's been no change in discovery. You could have given the Nobel Prize 10 years ago, it would have been exactly the same in terms of discovery. So I think it's not about the discovery, it's about other elements that comes together. Well, the first element is we're not the only one making breakthrough discovery here. There's a lot of people doing great stuff. So there is a bit of a bottleneck, I would say, in the Nobel Prize. So they have to go by order, and the order is not very clear to me. But it may just be that. Or it may be that they felt that the field needed to develop further in a way to be really established as a strong community. And it's true that if you look at the field, and we've seen that in many different meetings, I think in the last 5 years, the field has just absolutely grown exponentially. It's a different field in 5 years. And you see that in the amount of young people. When you go in a meeting, and the meeting we organized here in Cambridge, it's just amazing how many young people are there right now in this field. So there has been an appeal into the field, and it's possibly because if you look back, in the last 10 years, there has been a massive new series of new discovery. The big chunk come from the Kepler missions, and the Kepler mission was a fantastic tool to find so much planet and drive so much interesting result. So it's a bit this idea that in a way I do believe that the Nobel Prize is trying to reflect on the impact of the field, and they were trying to wait in some kind of point where they would decide to give that prize. But you know, they will never tell you. And we will never know. So make your ideas about what it is. But that's my understanding so far. Maybe it's completely wrong.
Question on the front?
Concerning the future study of exoplanets, do you believe that technology that's being developed right now, like the James Webb Space Telescope, and possibly future advancements in that realm, how do you think that those will affect the study of exoplanets, and do you think that it could help with increasing image resolution of the surface of these planets, or do you think that there are just fundamental limits to image resolution that telescopes can pick up?
Yeah. Okay. Well, there is a rule in astronomy which is very simple. It's give me larger mirror, I will give you more discoveries. Give me more wavelength coverage, I will make more discoveries. Give me more resolution power, I will make more discovery. Well, I think the James Webb Space Telescope, we are all of it. So I think we're going to make a lot of discovery, because it's just this. It's just better, bigger, it's just getting, you just observe in a new way. And then, when you add on to this, that as soon as you reach a limit, you enter into what's called terra incognita, and you are going to find something that is just will be a surprise, and maybe will drive the field in different directions. So James Webb will be a terrific equipment, and I think we should expect a lot of good stuff for exoplanet coming from James Webb. And there's a lot of transiting planets, and James Webb will just dive into that, and we'll try to get out the atmosphere of this planet, and who knows exactly what is going to be found in some of this atmosphere. I know we have beautiful modeling, but you know what I think about the models. It has to be challenged. So, yeah, it would be cool, it would be great. I really wish it would be launched and properly launched soon.
Questions? There is one question in the back there.
Not so much a scientific question, but more of a personal one. Do you think, or how do you think you would have to change the way you did your research or stuff on your career as a graduate student, or later on, if you had known you were going to win the Nobel Prize?
You know, there's something which I think was an amazing experience, and that in that sense I feel extremely fortunate. Most of the work of a scientist, and there's nothing bad about that, is you're confronting something which is known, and you do what's called incremental science. And most of the science is incremental, and for good reason, because most of the time you pretty know what you know, and you go a little bit beyond, because it's just a practicality, because if you go too far away, you don't understand anything anymore. So there's a practicality here. Now, in the case of the discovery, we were in a very strange and unique situation that to me was a unique experience. Is you end up with a set of data. It's really how it looks like, where these data are telling you a story, and the story that the data are telling you depends entirely on you, because these data are not the data that you get from the universe, is your translations what you get from the universe. You get something, wavelengths, whatever, and some information, and you need to translate that into something that you can understand, and it ends up as a data, whatever the data shape is. And then the data tell you a story, and the story that the data are telling you doesn't match anything. And you end up with a situation where you're back in this kind of concept where you're doing what is physics built on, which is built on observing the universe. You observe the universe, and then you conclude something. So the data tell you a story, and you conclude something, and the conclusion may be absolutely awkward. And in a way, the process we followed was pretty interesting, because when we had this data, we played a game to try to kill the planet. I mean, we've been trying to explain what we had in all the possible way, and it didn't match. But at the end, we had almost a situation where we said, sorry guys, we have to tell you, we found a planet. And it's going to be a problem, because it doesn't fit the theory at all. And I think it's a unique chance. So, from my perspective, what happened is when we made the announcement, I had a little bit of a panic, because I realized that practically I was responsible for this data. because this was my software, and it's this very complex software. We just barely started the experiment. We had just 1 year of experience on this. So everything was fresh. It was a new technology with a breakthrough in terms of the way we were using the hardware and combining everything together. It was a big jump compared to anything I have done before. And you end up in a situation that you're just holding on your data. If your data are just wrong, it just doesn't mean anything anyway. And I was really relieved and lucky in a way, because during this meeting in Florence, the Jeff Marcy team was there, and they had the telescope time at the right moment, and they observed the target. And 1 week after we made the announcement in Florence, Jeff Marcy sent us an email telling us, well, we confirm we have exactly the same period. And for me, it was a tremendous relief, because I realized at that time the data were right. Then you can argue forever about exactly how you want to see the meaning of the data, but data are right. So my experience was very profound at that time, because I really realized that whatever you think, go back to the basics and assume the data are telling the story. And the reason I tell the story is when we made the announcement, a couple of astronomers, professional astronomers in the audience, had this kind of bizarre reaction that said, oh, it cannot be true because the theory says so, which is, to me, not science, is doing theology, which is a completely different topic that I'm not willing to start tonight.
Take one question from here.
Just one classic question. How did you or how will we celebrate this one?
Sorry, say it again.
How did you or how will we celebrate when the...
Oh, how did we celebrate? Oh, it looks to be a never-ending celebrations, because I'm celebrating at any time and at any event. So we have a dinner after, it keeps going tomorrow, so it will keep going on and on. I've been told it lasts for 6 months.
So we'll take a couple more questions. We are way over time, but that's okay.
So you mentioned before that during these 25 years, our equipment and instruments have developed a lot, and we have made a lot of discoveries. And what about the theories? How are the theories now we use to predict or verify these discoveries different from 25 years ago? And how would you expect it to develop in the future?
Yeah, I think the theory had tremendously changed at the same time. I've been teasing the theory because we have been playing cat and mouse for 25 years, and we had this kind of joke. Then every time we would have a new meetings, we would announce new detections. And the theoreticians were there saying, oh, we have to come with a new theory to explain this new result. And the next meeting, they were very proud, and they started to come with a new theory, and they would say, oh, we can explain everything right now, this is what it is. And every time we say, oh, I think we have a new detection, and then the theory said, oh my God, the new detection doesn't fit the theory. It has been on and on and on and on for 20 years, really like that. No, it has to be stabilized, because they've been doing a lot of good work. And I remember one of my good friends, Professor Billy Betts, used to argue in his proposal to say, look, we can't predict what's going on in exoplanet theory. It's not because we're bad, it's just because we don't have enough funding. And he has been using this argument to get more funding. And he got it.
I like that.
You see?
Any questions right here? Then we'll take one in the back. Right here, behind you.
Thank you very much for a great talk and your talk. So I'm like one of the very few my colleagues who joined here from industry. So my question is, I think also following up on the question earlier, one of the reasons why you got this very great award is because you were dedicated for a very long time and you stayed in the academy. While some of us have sold ourselves to hedge funds, it's okay. So now you have a lot, you've been having a lot of sort of a lot of universities, and you have the power to possibly change something to make academy more, how to say, attractive.
Yeah.
Where do you think we can start from? Or would you actually do anything to make it more attractive? Because, well, you can think that I will just be the most educated people around me who don't care about money, who don't care about anything, and not necessarily even look for a lot of success because they are ready to, it's a failure. So, yeah, the question is, would you do something? If yes, then what, where would you start from?
Right, I think, thank you for the question. I think it's a very excellent question. So I think here there's different aspects to it. Well, the first one is clearly the idea that the university should be attractive to all the people that are interested by university is absolutely essential to university. Or if there is any red tape, or if some people feel they don't feel at ease for plenty of reasons, I think university has a problem. So university should really deal with that, and that, in a sense, it's a practical, there's plenty of practical elements to deal with that. But there is something a bit more profound, I think, in your question, is about the nature of the people working in research. And I'm building equipment, so I'm used to work by teams. So and so I think it's everybody doing that. It's not only about building equipment. I think science is a team play. It's not something you do alone, and the idea of the lone scientist and having all the great mind and all the idea, I mean, there must be some people like that, but most of the people, they're working in team. Well, the art of working in team is something that people in the business knows very well. I mean, if you do a monolithic team, it's not going to work. So I think the diversity of the team is, for me, essential. And the way I assemble team, and even the way I build consortium when I build with people, I'm not trying to find everybody the same. I'm trying to find the people different enough that they match. Well, you have to get a common interest. So I think the emotional element or the obsession has to be there. But I think the diversity, it can be on the approach, it can be on the background, it can be sometimes a cultural approach, the way you come up to a problem, or just because you have a different background and you're used to a different experience, is something which is essential. So I'm trying to do that as much as I can. Sometimes it's not possible, but I think we should strive to go this way because that's the best way to build up this kind of what I call the magic cement. There's an element at some point that everything goes together, and a team is becoming a dream team. And you make a dream team by assembling these people. There's a bit of magic when you do that. So I always experience that. I always experience a challenge, and that's clear that when you are PI of an equipment, so when you have responsibility, this is a very serious responsibility, and if you really take that seriously, and I try to take this seriously. So I think it's a very good comment, and that's an essential, the diversity is an essential element of the success in the science, in any academic, organized element, and I guess it's essential to industrial element, because that's how industry is being built. So thank you for the question.
So we are going to take one question at the back, but I want to ask one question following that, which is to zoom out a little bit. So we are in a sort of a privileged position here where we have the opportunity to pursue science and exoplanet science that too, and answer deep questions and all that. But if you take humanity at large, there is humanity all the way from the Amazons to the deserts of Africa to all sorts of places on Earth. And people grow up in very different circumstances. What do you think, in the most extreme cases, would be, even when for people, the economic reason is the most important thing to pursue? Why should someone pursue science in the first place?
Well, I don't think everybody should pursue science in the first place. I would be more in favor to try to strive on a knowledge-based society. I think the knowledge, for me, is the key here. And the knowledge apply not only to science, the different aspect that it applies, and I think fighting for the knowledge, fighting for trying to respect that knowledge, it could be a cultural knowledge, it can be a community knowledge. The science is an organized knowledge that is trying to go beyond by a mechanism which is built up. But I would not have all my eggs in the same basket here, but I would really insist on a knowledge-based society. Knowledge including art and music and emotions, so all these elements are knowledgeable. And I think a society which is respecting the knowledge, whoever the knowledge comes from, is a successful and a society where we feel at ease to live well. And we see it's not given, because we see that all the tension that society can build up, especially these days. There's a couple of examples we see, even in this country or in another country. It's very easy. I just learned that in the news that the Turkey decided to enter into Syria and to attack the Kurdistan over there. So I think this is something we have to face. So I think on a knowledge-based society, we have a task, we have a role, and as a scientist, we're just part of this process. So I would certainly not commit all the odds on the science. I will commit enough and having the science respected. Right now, the challenge for the science is there is a difficulty for the science to translate into the society, and we see that with the global warming. It's very interesting because there is no doubt that there's a global warming. I mean, you must be stupid to claim there is no global warming. There's so much evidence. But that's not the point. I think the people that claim they don't believe to that, I think they're not stupid. The translations to the society of this knowledge doesn't work. And I don't know why it doesn't work, and to me it's remains mysterious. And that's something that is related to the way you translate the knowledge to society, which is disconnected in a way, for some reason, which is still obscure to me.
So a knowledgeable society is the goal, and science is an offshoot.
Yeah, I think so, yes.
Take one question at the very back there, on the other side. Sorry. I'm sorry. So, okay, we'll take that. It's very, very hard to spread things around.
Just speak close to the microphone. Oh, no, it doesn't work.
I'm wondering if having had this experience of finding something really unexpected affects how you react to maybe your students' unexpected results.
Oh, giving it back. Good question.
Yeah, I think yes. Touché. I would love it. I mean, there are some students, my students in my audience. I don't know. I think there's a few because they were not able to register. It was so I hope I hope they would do it. I mean, I really hope. And I think they know. I guess they know me enough that I'm usually quite open. I like this kind of approach. I like the challenge, and I love when they come in with something that's kind of surprised me. So I think it's making my day. So please keep going it, because I think that's what it is. And it doesn't mean they're right, but it's good to surprise me. But you may be right.
So. All great questions. I'm afraid we're running late.
You're the chair.
So I would like to, before we end, I would like to thank Didier for being here and share a wonderful story with us tonight. I'd also like to thank the university and various departments in the university, all of which pursue exoplanet science. So we have Cavendish Lab, we have the Institute of Astronomy, we have the Applied Maths Department, Theoretical Physics, DMTP. And we have the Kavli
Earth Science
Institute, and we have Earth Science. So there are various departments across Cambridge that are entering into the exoplanet domain, and it's an exciting place to be, Cambridge, for pursuing this field. And the kind of culture, the intellectual and scholastic culture that we have here lends itself extremely well to pursue the kind of unsolved problems we're trying to pursue. Yeah. So it's a great moment to be here today, and let's thank our speaker once again.
ensemble is there quite quick, and you see that a couple of glitches, and I think they are really great. And thank you, Manu, for organizing it. I think this is.
I would like to give my special thanks to all my students here who you have heard on the game today, but that's fine. All my students who have done a wonderful job. Thank you, everyone.
So thank you.